Hello, everybody. Welcome to our first webinar of Sequestration Week 2 on carbon sequestration. I'm Joe Wachunas with Electrify Now, as always, here with my teammate, Brian Stewart. We'll introduce our panelists in just a second, John Perona. But so great to have you all with us for today's webinar. So if this is your first time joining an Electrify Now webinar, we try to electrify our lives in order to decarbonize. We see electrification as the clearest strategy to reduce our carbon emissions. And we try to boil that down in 4 steps. Number 1, to clean up your electric supply by buying renewable energy or installing solar panels on your home. Number 2 is electrify your home. So convert all your fossil fuel burning appliances into electric and efficient appliances. We have a lot of webinars that we've done to date to show you exactly how to do that. Number 3, electrify your transportation, your ride, be it electric car, electric bike. Make sure that you're using clean electricity instead of fossil fuels. And then number 4 is electrify everyone. We'll talk about that in just a second. Huge thanks to our over 40 members that are part of the Electrify Coalition. This is just a coalition of both for-profit and nonprofit organizations that believe in electrification as a solution to climate change. If your organization would like to join us, there's no cost to joining, just a quarterly meeting and adding your voice to this great group. So email Brian or I for more information on that. And then as you signed up for your Eventbrite ticket, you might have seen that we asked for donations for our Electrify Everyone project. Remember, Electrify Now is an all-volunteer organization, but we raise money for this great program and others. Our Electrify Everyone project is in partnership with the Community Energy Project, and we raise funding for heat pump water heaters that we install in income-qualified households that have natural gas water heaters. So we replace fossil fuels with clean, efficient heat pump water heaters. Last year, just our webinar series raised almost $4,000, and we've installed over 50 heat pump water heaters to date. And we just want to let you know that anyone who donates through the Eventbrite platform will be signed up to possibly win a free Climate-Wise landscaping book. This is by author Ginny Stiebolt, who will be our panelist on Friday. Really great book. I've bought it myself. So we've got 2 copies of that to raffle off to folks that donate. So extra reason to donate the Electrify Everyone program. Okay, folks, so this is Sequestration Week 2. Last March, we did Sequestration Week 1. And I'll put a link later to our YouTube page where you can find all those webinars. We did webinars on carbon capture and storage, webinars on forests. So if you don't see your favorite topic here this year, it might be in our YouTube recordings from last year. Sequestration week, we've had over 1,700 people from over 40 countries sign up for this week's webinars. We're so excited about that. If you feel comfortable letting us know where you're coming from, go ahead and put it in the chat room. We always love to see where our participants are coming from. And we also want to launch a quick poll. We love to understand where our audience is coming from. And so let me launch this poll really quickly. Okay, so we're gonna launch a poll just understanding where our audience is coming from. Are you part of the general public, the building industry, the nonprofit industry, government, academia? And while you are filling that out, let me just go ahead and tell you a little bit about our week's webinars. Today, we're going to be doing an overview of carbon sequestration. We'll talk about that in a second. Tomorrow, Tuesday, we're going to be diving into regenerative agriculture, which is going to be sequestering carbon in the soil. Number 3, we're going to go to artificial means on Wednesday, and we're going to be talking about direct air capture, directly capturing carbon dioxide out of the atmosphere. Number 4, we're going to talk about carbon sequestration possibilities in the ocean. And then number 5 is how we can do that in our own homes and yards with climate-wise landscaping. So you want to join us for all those. I'll put a link just in a second into where you can sign up for the remainder's week's webinars. So join us for all of them. And let me just check our poll real quick. Okay, I'm going to end the poll. I'm going to share the results. Oh, great. Very interesting. So most folks from general public, but 11% from the building industry, 21% from nonprofits, 10% from government, and 9% from academia, and 18% from other. So thanks so much, folks. Great data. Great. So, Brian, why are we focusing on carbon sequestration this week?
Thanks, Joe. So this is a huge topic, and of course, I think you got an idea just with the webinars we have coming up later this week on how many different chapters there are in this book, so to speak. But today we're going to be doing a great overview of that. But I want to just remind people at the beginning, because whenever we talk about sequestration, I think it's important to ground ourselves in this realization that the first priority is always about stopping man-made emissions as soon as possible, and those emissions primarily come from burning fossil fuels for energy, for heat, electricity, and transportation. There are other sources, of course, and we'll talk a little bit about that later during the week as well, but those are the main ones. And so most of the time in our webinars, we're talking about the solutions to this fossil fuels problem and helping people understand how we can transition quickly away from fossil fuels towards clean renewable energy, EVs for transportation, heat pumps, etc. So the first priority is to do this because the faster we do this, the less we will have to sequester. But regardless of how quickly we transition away from fossil fuels, there will be legacy emissions that remain in the atmosphere because we've been putting carbon up there for literally hundreds of years. And so scientists, just give you an idea of the quantities we're talking about. Scientists estimate that starting in 2050, we will need to have ramped up our ability to sequester carbon so that we can remove somewhere between 5 to 15 gigatons every year for a substantially long time after 2050 to continue to draw down, so to speak, the carbon that we've put up there over years and years and years. And just to give you an idea about that, last year in the United States produced about 5 gigatons of CO2. So it's a daunting task, but we have some time to get there. We've got roughly 30 years to ramp up to that level. And there's a lot of interesting things going on right now, which is what we're going to be talking about. And so it's just undeniable that some forms of carbon sequestration are going to be essential. And it behooves us, obviously, to be exploring all the various possibilities. And so today we're going to be talking about basically all the various types that are available to us and a little bit of an outlook on what their potential is, what's a little bit about what's going on in there and their ability to scale. But then, of course, we'll be getting in deeper on these topics in the next few days. So these general areas are natural solutions like forests, farms, and wetlands. There's ocean capture methods, like we'll have a topic on that specifically, a webinar on that specifically. Enhanced weathering is an interesting area. Then there's these more industrial areas like carbon capture, storage, and direct air capture, which we'll also be having a webinar on later this week. So we're going to give an overview of this today, the kind of these various techniques and how it's looking and potentially some of their potential for each of these. And we have a fantastic guest panelist today to help us give this overview. We have Dr. John Perona joining us. He has degrees in chemical engineering, biochemistry, and law, and he's the author of over 100 peer-reviewed articles. He serves on the faculties of Portland State and Oregon Science and Health Universities here in Oregon. His work focuses on the science-policy interface, specializing in climate change, the renewable energy transition, and biotechnology. He's the author of this recently published book, From Knowledge to Power, the Comprehensive Handbook for Climate Science and Advocacy. I highly recommend this book. A little out of focus, blurry. Anyway, we'll links in the chat. But it's a great overview of the climate issue, everything from what the problem is and what the implications of the problem are to what the solutions are, and also, interestingly and notably, what the kind of avenues we have to advocate for policies to advance the solutions as quickly as possible. So really happy to have John with us today. And with that, I'm going to turn it over to him to present.
Well, Brian, thank you so much for inviting me. It's a privilege to be able to address such a committed and large audience on this important topic. I actually carbon sequestration is actually the last chapter of my book, but it's certainly not least important because it comes up last. Carbon capture and removal from the atmosphere, as Brian is talking about, is really the only way we're going to be able to reverse these legacy emissions over time. And so this is a subject that needs a lot more attention than it's typically gotten. And I want to recognize that this is also a topic that has the potential to divide the climate advocacy community. Many of us are passionate in favor of carbon capture. Others don't necessarily think that it's an important approach to take. It's also tied in with the fossil fuel industry today. So an important theme in my book is the gaining of unity among the climate advocacy community, regardless of where we fit on the political spectrum, because we're all committed to solving this problem. And we know that there are forces in our society today that would prefer to keep the status quo. So let's keep in mind that we are all in this together, even if we disagree on some policies. So there's a lot to cover today. And it's my job to set the context for this week and all the terrific speakers that are coming up. So these are the topics I'm going to try to talk about this afternoon. What is a safe atmospheric concentration? Just a little bit of introduction about where we are and what the scope of the problem is. And then I'm going to talk about natural land sequestration, do a section on where we are today with industry, CCS, and policy. And then I'll finish off with the large scale carbon removal types of solutions. And I'll have to be pretty broad on all these topics to fit it into a half an hour or maybe a little bit more. So here's where we are today. The good news is that we are reaching a plateau. The rate of emissions increase in the last decade was a lot less than the decade before, and COVID is a blip there at the end, you see. But it looks like, even though if you kind of take that into account, the last 4 years or so, looks like we're almost at a plateau. We might be there. Time will tell. So that's the good news. But of course, the international agencies like United Nations and International Energy Agency are also reminding us that the current trajectory, while better than it was, say, 10 years ago in terms of the worst case scenario, the current present trajectory is somewhere between 2.5 and 3 degree world, which is far too high given the enormous impacts we're already seeing and that we will see between going from now to 1.5 degrees and hopefully not too much farther beyond that. Following up from that, the sobering news is that we can no longer reach a 1.5 degree C world without negative emissions, without some kind of carbon capture, whether it be along one of these methods that we're talking about. And you can sort of see that by noticing that the CO2 emissions drop in 2020 due to the pandemic was a little over 5%, but it now looks like we need on the order of 10% per year decreases if we were to be able to stay within a 1.5 degree world without overshooting it and therefore needing emissions to be needing CO2 to actually be removed from the atmosphere. So that's really not economically feasible. Nonetheless, it's our obligation to decrease emissions as far as possible to minimize the amount of legacy emissions we have to remove. So on this slide, you can see that where it says AFOLU right here, that's agriculture, forestry, and other land use. And where it says BECCS, that's a proxy for that's bioenergy, carbon capture and storage. That's a proxy for the industrialized methods that includes things like direct air capture. And so you can see here that in these scenarios, as you go from P1 to P4, there's more and more of a delay in initiating the steep emissions reductions, and that means there's more and more need for legacy emissions. So what happens if we actually get to peak CO2? And this is where we see that CO2 is really the primary problem, much more important than the other greenhouse gases, because levels are either a lot higher than them or because of the fact that CO2 persists so long in the atmosphere, which, for example, methane does not. So here we're seeing that once the emission stops, and the best case scenario today would be, say, we're at 420 now, we might get to 460 ppm. The best case scenarios might be about that. And then over time, you see on the left graph, the decrease in concentration, a little bit steep in the beginning, but then leveling off. In the year 3000, the CO2 concentrations, depending on how far we go before we stop, still well over pre-industrial, and the temperature decrease quite modest. And given the impacts and the potential for going over tipping points, we really need to be able to decrease emissions as fast as possible, while recognizing that we also need these technologies to remove the carbon from the atmosphere. So what's a safe level of atmospheric CO2? And the answer, of course, is we don't really know. But there's a sobering warning here from this. This is coming from paleoclimatology. These are data from the Antarctic ice cores. And the red arrow at the bottom right is showing where we are in terms of the last interglacial period, which is a period of Earth time, which is as similar today as we're going to be able to get in the past. And so what we're seeing there is that we had, based on these data from the ice cores, oxygen isotope record, and other geologic evidence regarding sea level, we can see that the sea level was about 6 to 8 meters higher than today, and the temperature about 1 degree higher than today, even though atmospheric CO2 was below 300 ppm. Now, there's a lot of complication in this. The insulation of the Earth is complex, depends on cycles, astronomical cycles having to do with other planetary bodies that are not fully understood in terms of their impact on our climate. Nonetheless, we see here that even concentrations well below where we are now were enough to have sea level rise very high. And that should make us think about the need to really reduce CO2 quite far compared to where we are right now. And so if we ask the question of, how much CO2 do we need to remove? As Brian mentioned in his introduction, about 5 to 15 gigatons per year of CO2 by mid-century is sort of where the technology needs to be. And this slide is showing cumulative CO2 emissions on the left, and then the residual emissions that we still can emit given the carbon budget that we have to stay within 1.5 degrees. And so this is showing a scenario where the drop-off is really very aggressive. We've done a good job of mitigating emissions. The temperature in the year 2053 in this scenario is somewhere between 1.5 and 2, maybe it's 1.7 or so. There's some residual emissions to account for, and then there's a choice. There's how much overshoot do we want to allow? In other words, if we're going to mitigate to get to 1.5 degrees, then we need to remove a certain amount of carbon from the atmosphere. But if we want to mitigate further than that, and we want to reduce CO2 levels farther, then clearly the amount of negative emissions that we need to remove, the amount of emissions we need to remove from the atmosphere, the CO2 removal, it gets a lot higher, right? So how much we need, we can't say for sure, but we know it's going to depend on when we finally reach net zero. What is the temperature in that year? What are the impacts we're experiencing? And how fast we want to decrease the temperature after that? And to what level? Will it be acceptable to stay at 1.5 degrees C over pre-industrial over time? Or is that not acceptable? So, and I should mention here that the scientific community, the modeling community, bears some responsibility for the sort of negative perception of CCS that some folks have, in the sense that for a long time, the targets in the models were for the year 2100. And so that scientists tend to try to use the same standards so they compare the results to each other. But by setting the target year at 2100 and saying we need 1.5 degrees, say in the year 2100, it really allowed the models to delay emissions and then bring in the negative emissions later, to delay emissions reductions, and then to bring in negative emissions later. And of course, what that would do would spike temperature higher by mid-century, right? So it's pretty clearly recognized that that was a mistake in terms of setting that target so late. And so now it's really clear the message from the scientific community is negative emissions are not a substitute for aggressive mitigation. Okay, so I'm going to talk about some of these different methods, starting with the natural emissions, the natural ways of sequestering carbon, which are forests and farms, basically, most important ones. And so these are data from the IPCC's land report in 2019, which shows averages over the prior decade. So the average emissions per year and the portion of that that's coming from forestry and other land use, so land use change, you can see the numbers there. So a lot of that human emissions from forestry and other land use is, say, deforestation. But the land is still a net carbon sink. because it is operating to remove the emissions that we are putting out into the atmosphere in the form of CO2. So the land is taking up on average about 29% of our emissions. The oceans are taking up another quarter of our emissions. So about 45% of our emissions remains in the atmosphere longer than a decade, for many decades, centuries, millennia, even beyond that. So we would be in much worse shape if the land were not able to take up at least this much emissions. So every year in this period of time, the land carbon store increased by 6 gigatons of CO2, which is a lot, right? So it's doing a lot for us. And the question is, can it continue to do that? Can it continue to absorb even more, right? Or are there limits to that? Right. So this is a terrific paper published in Science Advances in 2018, which shows the technical potential as of 2018 for carbon removal by natural means in the United States. And we can see here that the largest potential savings are from reforestation and properly managing our forests. And then there's also significant potential carbon removal and sequestration from agriculture and from grasslands. And what's nice about this study is that it shows that the technical potential is really quite high, that it's over 20% of the total emissions that we put out in the year 2018 could potentially be sequestered by 2025. That's no longer the case because we're halfway to 2025 and we haven't been really doing this at anywhere near these levels. But another nice insight from this work is the cost, and in terms of a carbon price per ton of removal, right? And so you can sort of see on the right that there's some easy emission savings in reforestation and forest management. A lot of those will cost on the order of $50 a ton, and there's some quite difficult emissions in reforestation that it will cost a lot more to be able to remove that much more at the end. And on agriculture and grasslands, you might note that a super inexpensive and very effective solution is cover crops, which can be had for on the order of $10 a ton. This is very helpful and informative in terms of thinking about, where policy should be. So cover crops, great. Biochar, not so much, right? Okay, so we can make some distinctions around any sort of land-based carbon sequestration policy. Do we want to preserve the existing stores versus removing atmospheric carbon? Different approaches will do one or the other of those. Do we need new land use? Or can we just simply better manage existing land? And how fast will the impacts of the sequestration be felt? So for example, if we want to do reforestation, we're certainly removing atmospheric carbon. We need new land compared to where we are now. And this is a nice map of where the potential is in the United States from that paper, but it also has a delayed impact, right? Because it takes a long time for a forest to grow and soak up the carbon. On the other hand, if we're just improving forest management, the impact will probably be a lot faster. Principles of managing forests: greater forest complexity, meaning diversity of types of trees, diversity of leaf types, diversity of heights. Make the canopy complicated so that it absorbs the most possible sunlight and fixes the most possible carbon. And then the other principle is use native vegetation as much as possible for the reasons I've listed there, not the least of which can be public acceptance in getting the policies put in place. We need to recognize that something like 60% of US forests are in private hands, and so our policies need to reflect that. Most of the rest is in federal hands, so we can amend the federal laws like the National Forest Management Act to require explicit carbon storage in the forest, as opposed to the sort of more general maintenance policies that we have now. And then funding for conservation easements, and negotiations with timber companies so that they recognize the value of a sustainable forest for their profit stream, as well as preventing leakage of the markets to other countries where environmental safeguards are likely to be less well established. Right? So here are the cover crops, a terrific, inexpensive method to sequester carbon in agriculture. Limit erosion, increase water infiltration, improve the soil structure, get more organic matter. You need less fertilizer. every farm in America should be planting cover crops. The kinds noted there are the most popular ones. And there are many other approaches in sustainable agriculture that would lead to the reduction in fertilizer use. Fertilizer is really a huge climate burden in the sense that it costs a lot of CO2 to make it in the first place. And then once the fertilizer is applied, it really unbalances the nitrogen cycle, and it puts up a lot of nitrous oxide, which is a very potent greenhouse gas. Right? And I love the way Michael Pollan talks about this in The Omnivore's Dilemma. He emphasizes how it used to be before industrialized agriculture and animal husbandry, that animals and plants were integrated on the land. And so they're basically making a cyclical process so that they're using up each other's waste streams. Now we've separated these. We've got an industrial process here, an industrial process here, each of which is generating enormous pollution and climate detriment. So that's something to think about. I don't have a solution for how to get back to that, but I really think Michael's book does a very eloquent job of describing what we could be doing in agriculture. And so, stepping back a bit to finish off this section on natural land management, there's a concern about how long the land climate sink can continue to keep on taking up carbon. And there's some recent papers that suggest that the tropical land sink especially has saturated. The African rainforest here is shown steady through about 2015. The Amazon rainforest is decreasing, but the modeling in that paper here in Nature, this paper here on the top, suggests that the African tropical forest is following the Amazonian. We're still adding carbon to the land, but the tropical forests, which are taking up about half of the human emissions that the land can take up, have peaked in terms of their carbon absorption. Similar problem with soils, where in tropical soils, the warming is releasing the carbon. So I don't want these sorts of studies. I mean, there's really a developing literature that is suggesting that the capacity of the land to absorb carbon is limited. The forest carbon does saturate over time once the forests are fully grown. They're holding a lot of carbon. We need to preserve those, like in our old growth forests, but they're not adding more carbon over time. And then, of course, the effects of climate change are themselves hurting the ability of these natural land management methods to keep carbon in the soil. We do have some benefit from CO2 fertilization, but it's offset. Increased respiration in the soil, which puts the CO2 back out, and some of these other limitations associated with nutrients. So I don't want the message here to be, don't work on natural land sequestration. Clearly, every approach is important. We can gain a lot from doing better forest management, increasing forest plantings, especially in temperate regions, and doing sustainable agriculture for sure. But in the big picture of things, right, and this is really what I'm trying to focus on here, in terms of getting our legacy emissions ultimately fully reduced down to levels where we have a safe climate, it's really unclear that we can continue to count on the land to do so much for us. In other words, emphasizing the more industrial methods, the importance of those. So let me switch over and talk about carbon capture and storage and utilization, which are these two sides of the coin. CCS is what's going to be important for the long-term management of the climate. But here you can see emissions from manufacturing electricity can be captured in industry smokestacks where the concentration is very high, so they can be very efficiently captured. And then the capture can either be, the companies that capture the carbon can sell it into markets, or they can bury it. And here the burial can be either in saline formations, where it's stable over geologic time, or unfortunately, the way the industry developed, a lot of the market now is for what's called enhanced oil recovery, which you see on the left bottom of the slide, where carbon dioxide is pumped into sort of spent oil and gas reservoirs and pressurizes them. The carbon is sequestered; it's stable under there. It's not that there's a zero climate benefit, but clearly it's offset by the fact that it's being used to take oil out, which can then be burned, right? But that's the reality about how the usage industry developed. A lot of these uses are very transient in terms of the CO2. There's no sequestration at all. If you take CO2 and put it into a carbonated beverage, there it goes as soon as you open the bottle, obviously. But many of the other uses can be pretty permanent geologic sequestration. Enhanced oil recovery is one of those. Another sort of stable long-term storage solution that goes under the carbon capture and usage sort of headline is cement manufacturing, where you can sort of cure cement, leach out the calcium. That's on the upper left of this slide on the bottom. And so once the calcium is leached out, if you pump in CO2, you form more calcium carbonate in the solution, which mineralizes inside the cement. And so it's a way to take CO2, capture it from the atmosphere, from a smokestack, pipe it into a cement operation and incorporate it into the cement. And so this was included in a report to Congress which was mandated from the Council of Economic Quality in Biden's White House. So why CCS? And simple answer is that we have many industries today that are yet to be electrified and that are difficult to electrify over a very short period of time. And so in the interim period, until they can be electrified, and we think that probably most of them can be, but until then, we can either let the emissions go or we can capture and bury them. So I think it's clear that we ought to be capturing and burying them to the extent that we can. There are a number of industries where this is important. And naturally, we would like to improve process efficiencies. If you make a process more efficient, it'll emit less. That's something we can do. We can also try to find green methods and green alternatives. We should certainly do that. But for a lot of this, those approaches either reach their limits or we haven't been inventive enough yet. So we should capture and store the CO2 while, of course, also minimizing the amount of fugitive methane. Most of these processes are going with natural gas. There's a lot of problems with upstream methane emissions in the natural gas industry, and we definitely need to tighten that up, right? But that's not a reason to not use CCS. Hydrogen is another important area of the economy where we should be using CCS. If we switch from gray to blue hydrogen, where blue hydrogen is decarbonized because the carbon has been captured in CCS, then we save a lot of legacy CO2 emissions. Ultimately, we want green hydrogen at the bottom left of the slide. But right now, it's way too expensive to be economically possible. If we do have excess zero carbon electricity, we certainly need it to be staying on the grid and not using it for other applications, because the number one thing we need to do is make the grid as green as possible. Right. So we want to go to green hydrogen, but in the interim time, we can save a lot of legacy CO2 with blue hydrogen. And you can see on the top of this slide, just an example of all of the possible industries where hydrogen is used today. It's a very large source of emissions, and we should be trapping that. One of my favorite applications is long duration energy storage on the electricity grid, which addresses solar wind intermittency. I recommend this paper. It just came out. It's an effective rebuttal to a paper by Jacobson's group that was really very negative on blue hydrogen. Some of you may have heard about this study, but that study used a lot of pretty biased assumptions against the technology, really against the possibility of the technology developing in such a way that we can capture the fugitive methods and we can use new approaches to get more and more efficient with the blue hydrogen technology. So, another area that's difficult to think about and is controversial has to do with, should we equip natural gas power plants with CCS? If we do that, we're taking market share away from wind and solar, which are our preferred solutions. And we're still always going to have some amount of methane leaks, no matter how good we do with capturing fugitive emissions. On the other hand, are we going to be able to add wind and solar at a rate fast enough, given also the challenges associated with long-term energy storage on the grid, which we really don't have hardly any of right now. Another issue is that for peaking power, when demand goes up, the very best solution now is natural gas, because it's very dispatchable and it's widely available. We don't really have an alternative to that either. In Oregon, we have a very aggressive emissions reduction law from the electricity sector. Are we going to be able to meet that without CCS on natural gas-fired power plants, which provide about 40% of our electricity now in the state. It's not clear to me whether we can or not. Okay, so moving to how CCS works. CO2 into flue gas, so let's say it's 10% CO2 at the bottom left of this drawing. It goes up this tower, and trickling down the tower is an amine-rich reaction. The chemistry is shown here, and amine is this class of chemicals that react with CO2 in the reaction shown. And rich amine coming out the green column at the bottom, then goes through a heat exchanger, and the amine is stripped off the CO2 and recycled because it's expensive. And then at the top right of this drawing, you see purified CO2 output. The capture rate is typically on the order of 90%. There's an economic sort of point where that's an optimum. It's very clean, and it's immediately pressurized and then can enter a piping network. So once you have CO2 extracted, it's transported under pressure in a supercritical state through pipelines to its storage site. This would be how CCS would work. Right now, we've got about 5,000 miles of CO2 pipeline. It's almost all developed for the enhanced oil recovery industry, and we need a large expansion of this. Congress, however, luckily just passed in the infrastructure bill this what's called the SCALE Act, which gives a lot of financial incentives for companies to build the CO2 pipeline infrastructure. And this just shows you a map for the central part of the country of what's envisioned. The good folks at Princeton Net Zero America, who have produced probably the most granular model for the energy transition in the United States, have laid out how much it costs and how much pipeline is needed. That's a very small fraction of the total fossil fuel pipeline infrastructure in the United States, by the way. So I don't think there's much doubt that we can build this pipeline infrastructure out. And then finally, where does the captured CO2 go? It gets injected under pressure very deeply into the earth in either the oil and gas reservoirs or these underground saline formations, which are basically permeable reservoirs under impermeable rock. The CO2 stays in its fluid state. It gets into the interstices of the rock. Eventually, it mineralizes over a period of decades or so, and it's really very secure under there, whether it's an oil reservoir or saline formation. And there's huge area of saline formations available. Compare what's available for storage in the US to what our emissions are, and you see that there's no problem finding room for the emissions. True, a lot of this is EOR. That's kind of been sort of like a deal with the devil in the sense that in order to get policies, which I'll show in a second, negotiating with the oil companies who insist on this EOR provision, it's at least better than taking the CO2 from underground caverns, where it actually exists, and then using that CO2, because then you're not capturing anything. So now there's at least some small benefit associated with EOR. And this process of injection is well regulated by EPA under the Safe Drinking Water Act. So this is where we are with CCS today in the United States. There's a grand total of 12 projects. 11 of them are EOR, but one is dedicated to geologic sequestration. And if you look at what the US has done in terms of present operations, it's about half of what the world has done. The world total is now about 0.04 gigatons CO2 per year. And as we've said, we want to get to on the order of 10 gigatons per year. So we're between 100 and 1,000 times short, but we do have time to develop this, and the climate can stay safe as long as we also do the very fast emissions reduction, right? So we have policies on the books now. Congress is now paying attention to this. The production tax credits for sequestration in saline formations where it's not anything to do with the oil industry is going up to $50 a ton by 2026. We have some credits for the oil industry for EOR, a lot of money for research and pilot projects, incentives to build a pipeline network, and there's potential additional avenues for support, as you see, one of which, Bill, is to increase the credits even more. This is getting into some serious money. And so it should be a good spur for CCS in the next decade. And California has also led the way at the state level with the low carbon fuel standard. You can get credit in that program for CCS. Okay, so I'm going to finish up probably out of my time already, but I'm going to finish up quickly by talking about the sort of longer term approaches to the problem of atmospheric carbon removal. And I'll just mention the 4 approaches that are on this slide. And I want to emphasize, kind of conceptually, what's going on here. One important aspect to note is that the industry CCS underlies direct air capture, because it's a lot of the same technologies: amine capture, CO2 pipelines, CO2 storage sites are common between industry CCS and direct air capture. Direct air capture is a lot tougher because it's so dilute in the atmosphere. And CCS is really mitigation, some form of mitigation. It's like building a solar farm or a wind farm, because it prevents CO2 release, right? Capture it and bury it. On the other hand, these direct air capture methods and some of these other methods are not really mitigation, because the CO2 is already out there having its negative impact, right? But at least they're addressing the root cause of the problem, the human-caused energy imbalance, right? And we can distinguish this from solar geoengineering, which is certainly not mitigation. But not only is it not mitigation, it doesn't address the root cause either. What it really is some form of adaptation, where we're going to put sulfate aerosols in the atmosphere. We're going to do that continuously over time, which is quite problematic. And then we're going to sort of hide underneath this shield, which makes the Earth more reflective and therefore cools the planet until such time as the shield might go away, right? So it's kind of like a seawall. You can hunker behind the seawall and hope that things will be okay, but it's not solving the problem. And this is a pretty problematic approach, which I'm certainly not advocating. Although there are many people now who are thinking that we might need to do this in the short term. Okay, so a couple of the methods. Direct air capture is shown here in these sort of tubs. Ambient air is captured, basically a lot of fans, and I know you'll hear a lot more about this from later in the week. A lot of fans to push air over these capture columns. Chemical solvent or sorbent, CO2 release, basically the same, in qualitatively at least, the same kind of stuff that we talked about with CCS, and then compression, transport, storage of the CO2. Right. The great thing about direct air capture is that it has a nearly unlimited potential because of the great size of the underground reservoirs that are available. You can also put the direct air capture facilities anywhere. So why not put them right over the geologic reservoir, thereby minimizing the need for CO2 infrastructure and pipelines, right? It's expensive. It's very energy intensive. We obviously can't use a carbon emitting source for it. So those are among the challenges right now. It's quite expensive, energy intensive, and it's going to need more in the way of public subsidies. Even the enhanced tax credits are not enough yet to drive the direct air capture industry. But over time, especially if we gain more and more experience with industry CCS and get better economies of scale going and more innovation in the technologies associated with industry CCS, they will transfer over and make our job easier later, right? Accelerated weathering is a really interesting idea. So these are some of the reactions that weather CO2, basically remove CO2 from the atmosphere by reaction directly with rocks. Normally, this takes very long periods of time, on the order of hundreds of thousands of years, or at least tens of thousands of years. But if you crush up enough mineral aggregate, rock aggregate, and spread it out over a huge surface area, it's all about the surface area. It's been modeled that this can actually be a scalable potential method for removing CO2 from the atmosphere, even though truly enormous amounts of minerals are needed for this. And so, basically it's mined reactive right, it's mined tailings, different kinds of reactive materials. The limit is, how much aggregate rock is produced in the United States. But there's markets for it also. So that's a potential point in its favor. Bioenergy with carbon capture and storage is interesting. You use biomass feedstocks, make electricity from them, or make ethanol by fermentation from them, and then capture the carbon and bury it. Right? And then, the biomass regrows, and the carbon, these harvest it again, used to make electricity, bury it again, keep on going as far as you want. It looks great on paper. The problem is that there's really been no attention to the enormous amount of material that would be needed to do this at scale, the development of the supply chain. There's no public conversation about this. This looks great on paper. I really have trouble thinking that the conflicts with other land use that would be involved would not block this at a large scale. But others, have different perspective on that. Clearly, we need land for food. We could use land for biodiesel. I think that's a much better option if we're going to use the land for energy. But nonetheless, this is out there, and it's got a potential that could be very high if we were willing to bear the burden of the land use change. Right. And finally, there's a new report from the National Academy of Sciences involving a research level description of about 6 different ocean-based carbon dioxide removal approaches, all of which are at the research stage now. And these are just some of them. Nutrient fertilization is the farthest along in the sense that we can, if we add iron or other nutrients to local regions on the surface of the ocean, we can increase phytoplankton growth, and that will eventually enhance what's called the biological pump, just shown here. The phytoplankton will sink to the bottom where it says organic matter. This is actually the source of all the oil and gas we have today, these tiny microorganisms. So we could use this natural process if we could seed the oceans with the nutrients needed. Right. So it's problematic. We don't know the effects on the food web. We don't know how scalable it is, but that's what the research studies may show us. And among these other methods, I'll just mention that ocean alkalinity enhancement is an interesting approach. It can couple to the enhanced weathering that I just mentioned, put some of those minerals in the sea where they absorb CO2. They will release bicarbonate, and that is an effect that will tend towards alkalinizing the ocean. And therefore reduce acidification and bury carbon maybe at the same time. Right? So that's the potential of that sort of coupled approach where you could use the ocean. Okay, so that's all I have for you. Thank you so much for your attention. And I am going to turn it over to Joe and Brian for questions.
Thank you, John. That was fantastic. Yeah, so I want to, there's so much to dig into here, but maybe just to start out with, I just want to go back to this 5 to 15 tons kind of range that we were talking about in terms of what we were going to need to be doing starting around 2050. And obviously a lot of scaling up to get there, because we're not going to just be able to throw the switch in 2050 and do 5 gigatons a year. Right. How does that number, how does the land-based methods we were talking about, forestry, forest management, reforestation, agriculture, is that included in that 5, or are we thinking that 5 to 15 is in addition to what we might do if we manage the land properly?
No, it's included in that 5. And, I emphasize that, the concerns about the land saturation limit, they haven't been borne out yet. We do have some reasons to think that the land sink will not be able to provide all of that 5 to 15, certainly not year after year once the forests sort of saturate with carbon, but they can certainly contribute to it. Right. And so, and those methods also will cut down the amount of land use change, which now is adding CO2, right? Because right now, something like 15% of the CO2 burden comes from land use change, things like deforestation. So just stopping that will itself already be our problem.
Is there anything that gives a kind of like a rough idea of of that 5, let's just pick 10 as an easier number to work with. Any thoughts about what the sort of natural methods might produce, as a part of that? I'm just trying to get a rough idea.
You're asking, that's asking a lot. If I were to just give you off the top of my head guess, I'd say maybe a quarter of it might be able to use with natural land approaches. There's some of these studies in terms of the technical potential, they're really very promising, and it's going to depend on policy. If we're willing to pay farmers and private landowners who own forest land to keep the carbon sequestered, and there's no doubt that we can afford to do that if we want to. then we can get closer and closer to our technical potential, and which was really pretty high. I mean, that was 20% of the U.S. emissions there. So, some of them may not be additive to each other, but I think most of them probably are in that particular study. Yeah.
Well, I think the other thing that, and you pointed out in your slide there, is that one of the interesting things about the land-based ones is they tend to have all sorts of really excellent side benefits.
Exactly.
Better water, better cleaner air, better biodiversity, better for plants and animals in general.
Yeah. Yeah, we need to be careful with land always, because there's so many values implicated around besides just climate. And so we see that in the sense that we can improve get these other benefits. But there's also there are equity implications associated with land use change, and there's it's a place-based thing for people get very naturally and appropriately attached to how land is used and allocated. So methods like biochar are they could improve the soil, but the land use implications of having to harvest all that biomass year after year make it challenging to think about.
John, pivoting maybe to some of the artificial methods, and I would encourage our listeners maybe to put their questions instead of the chat, put it in the Q&A. It's a little easier to track the questions there. But one listener says that the CCS adds about 14 cents a kilowatt hour to the wholesale cost of natural gas. Any questions on kind of cost effectiveness of CCS and direct air capture, which you mentioned already a little bit?
Yeah, well, I mean, there's no question that adding these extra operations to the facility costs money for the development of the facility, and so then there's a recovery of that in the electricity rates. So I think we need to use properly equitable policies in assigning electricity costs so that we mitigate that to the maximum extent that we can. If we could implement carbon tax, for example, and return part of the money to households, then we would be able to have a way for the companies to be incentivized to do CCS, right? And then the dividend return would help the folks pay the higher cost. So, I think a lot of that has to do with how you do it, what the policy is.
There was a question, just to remind people to calibrate on this 10 gigatons we were talking about per year. The reference point that I think is most useful is the United States in 2020 produced 5 gigatons. So basically, if you can kind of get it's so hard to imagine these quantities, but if you can sort of imagine all the emissions that the United States produces in 1 year, we have to figure out a way to take all of those emissions back out of the atmosphere every year. So it's a huge number we're talking about.
But that's also a global number, let's remember.
Yes. It's not just
the U.S. contribution is 5, but we're also only putting out 20% of the global CO2 or something like that. So
I had a question for you about enhanced oil recovery. EOR, some people, if you're confused by the acronym, it means enhanced oil recovery, where we're capturing the carbon, the CO2 from the emissions of burning the oil or producing the oil, and then we're using that to pump back into the ground, to pressurize the oil to get more out of the ground. So if you were doing that same operation, but you're pushing the carbon into those same reservoirs, those same piping that already exists, but you weren't extracting the oil from it. So I guess that would mean you're actually increasing the pressure under the ground by pumping the carbon in there. Is that doable, or do you have to push the carbon into different places? These saline aquifers you were talking about, those are not the same geographic or geological formations as the oil is in. Is that correct? These are different.
They're different, and the limit and the capacities of the EOR reservoir or the oil and gas residues are much smaller. If you go back to that slide, than the capacity of the saline aquifers. I don't know the answer to your question, and I don't know that anyone has, tried to use an oil or gas reservoir as a pure sequestration site without also taking out the oil.
Mm.
I suspect that it should be possible. I don't know. I haven't seen anything that suggests that the nature of the underground reservoir is so different that you couldn't just not have the oil extraction pipe and it would still work. But I don't know for sure. That's a question for an industry
Okay.
engineer.
John, Steve has our first question in the Q&A that kind of gets to something that Brian and I have been talking about a bit. He says, is there a local action option for individuals and small businesses, or is this all just a giant research dependent? And before answering that, I'll just say, we did try, Electrify now is very heavily about DIY. How can you take some of these matters into your own hands and help the situation? And on Friday's webinar, we're going to be talking about sequestering at home. But any thoughts, John, on what individuals can do to take part of this in this sequestration movement?
Well, sure. I mean, one option could be to buy renewable energy credits in your which can be done by businesses or individuals, and that's a way to have all of your personal electricity be purchased as renewable energy. And then if you're a business, you can display that and say, this is a green credential of mine, and folks who care about green credentials will differentially buy your product and probably more than offset, the extra cost associated with that. I mean, that's one option that one could take. And, there's also, especially on the land stuff, it's true that these industrial things are still more at the research stage, but in terms of land, funding conservation easements, basically that set aside private lands, and basically the private owner, which is 60% of the farms and forests, private owner agrees to not to use their land in such a way that it causes carbon to be released from it. Right.
Yeah, I think that's a good point. I mean,
but pay those carbon, buy conservation easements. And there are,
a lot of the affordable carbon offset products are land-based sequestration products in general. I think there's a lot of reason to be like question how effective they really are, but on the other hand, the ones that are highly vetted and ranked and scrutinized by the bodies that do that are probably pretty good investments in terms of helping to improve our land-based methods for carbon sequestration.
Right. There's a lot going on in terms of voluntary offsets by companies to enhance. So there's a law called the Growing Climate Solutions Act that was passed with bipartisan support in Congress that connects farmers with offset programs or voluntary programs from industries, so that there's a way to put the money from the company and the farmer, who may not know all the details of these carbon markets, right, put them together so that something actually happens on their land. And you're right that this does require a lot of oversight to make sure that, for example, whatever happens is something that's actually new and wouldn't have happened anyway, right? Verify that it actually does happen.
One of the things I was wondering if you could comment on, because I think right at the beginning, you were mentioning that there are people who are suspicious about sequestration technologies or solutions, and can you just give I understand that right now that there's I can see how if when we're seeing carbon capture and storage basically being used by the fossil fuels industry to perpetuate their business model, that smells bad. But apart from that, what are the other reasons that people might be have a negative opinion about carbon sequestration as a
Well, I mean, it looks like, it's what's called moral hazard. The idea that if we're going to be able to bury all our emissions eventually anyway, then who cares about what we do right now? Let's just maximize our, throw caution to the winds, burn all the fossil fuel we want, and, we'll just solve it later with technology. And, that is something, as I mentioned, that kind of, obviously it wasn't deliberate. It was kind of, came out of a choice to use 2100 as the target year for, when we want temperature to be at a certain level. But the choice of that for some time led to, the sort of the burial of these negative emissions technologies inside of these models, and this quite slow decrease of emissions, say to mid-century, and then faster decrease, and then building up all this carbon negative. So that it's not and so I think the modeling community bears some responsibility, but I think they've also owned up to that now and recognized that that was an issue. And so I think there might be some residue from that.
Yeah. I can see how there might be some people who you could have the opinion that $1 spent on carbon sequestration could perhaps be spent better on carbon avoidance at the moment. So I think we have this weird dilemma where we basically can't spend enough money on carbon avoidance right now, because the quicker we transition away from fossil fuels to these clean renewable things, and it takes money to do that, the quicker we do that, the better off we're going to be. So I can see how you can get your head in we should spend all our money on that. But if we don't spend money on these carbon sequestration research and technology development, we'll never get them developed, and they may take decades to develop. Yeah. So it feels like you got to be doing both at the moment to some degree.
Yeah, I mean, well, one way to do both at the same time is to improve land-based sequestration of carbon so that we contribute less in the land use part of our emissions. Right? Because now you're doing both. Now you're keeping carbon on the land, and you're, because we still have 15% land use, 85%, greenhouse gas. Well, that 15% should go as close to zero as possible. Right. So that's both at the same time.
I just want to remind, we got a lot of questions about the ocean and a couple about soils. We're going to kind of save those questions because we're doing deep dives on those in the rest of the week. So join us for our soils webinar and our oceans one on Thursday. Soils is tomorrow. I did want to, sorry, where was we? Angie wants to know, all these carbon sequestration solutions are storing carbon, whether they're natural or artificial. How much of that is a problem when we're factoring how long carbon will be stored and whether it'll leak back into the atmosphere?
Yeah, so the natural land approaches have a problem with transience, because even a long-lived old-growth forest is not forever, right? And a lot of the agricultural methods, it depends on good policy as well from year to year. It's no-till agriculture, we're saving carbon. Next landowner on that land doesn't care, goes ahead and tills it, all the carbon is gone. And then of course the natural land is susceptible to all the ravages of climate change itself, right? So it's intrinsically more transient than the geologic sequestration methods, which so far have not shown any appreciable leakage. And I mean, we would know about it. The EPA is, carefully regulates these injections. Geologic is, as far as we know, very stable, long-term, millennium, for basically forever.
Could you touch just on that the EPA kind of oversight you mentioned, because I can see how at some level pumping CO2 into the ground feels a little bit like fracking, and from the standpoint of there is a lot of weird byproducts of that pushing water down into the ground that have proved to be pretty disastrous in some communities in terms of so can you just speak a little bit to how confident we are that this pumping CO2 in the ground doesn't lead to some weird byproduct problems like aquifer pollution, or I don't know what else it could be?
Yeah, well, that's part of what the monitoring that the EPA requires will do. Is monitoring for emission for the CO2 coming back out. We're also monitoring groundwater and drinking water, especially these injections are way below those water tables typically, and also they're not fracturing rock in the same way that fracking technology does. And we've seen this great increase in earthquakes in fracking zones. I mean, fortunately, they've been mostly low-level earthquakes, but there's this clear, huge increase in response, and we don't have that happening in response to just this sort of injection. So it is fundamentally distinctive technology.
That's reassuring.
Which is not to say that we don't need to keep our eye on it.
Yeah.
Right, but one potential positive is that the scale of availability of these underground aquifers, especially in North America, is so huge that if some sites are problematic, it won't matter. We can go somewhere else.
That's great.
Yeah.
Joe, any other questions are popping up to you?
I think we've gotten to good themes here. We'll take the questions from the Q&A and shoot them over to John and see if he can help answer any of the ones that we didn't get answered, if that sounds good.
John, is there anything we didn't ask you that you wish we would have asked you? Any questions you want to answer that we didn't ask?
I think we've got. I'm just taking a look through here. Is EOR a net benefit for the climate? That's a tough question from Rob. The good folks at the World Resources Institute, and I recommend you read everything they publish, think that it is a small net benefit because of the alternative of dredging CO2 up from underground caverns is such a detriment. And there's more buried than they make, than is later polluted by burning the oil that's extracted, but it's not much, right? I mean, having our druthers, we would not, we would certainly not choose to subsidize with tax credits, the oil industry's enhanced oil recovery for the extremely minor climate benefit it brings. This is where, we get into another level of controversy around, how pure should we be in our advocacy? I mean, is it ever okay to negotiate with a fossil fuel company, given what they've been doing and lying to everyone about climate change? Or do we have to face reality and say, okay, take your tax credit for EOR, give us a bigger tax credit though for the burial in the underground aquifers? So that's what's happened, right? Let's see. Why not focus our efforts on green hydrogen infrastructure instead of blue and gray hydrogen? Absolutely. Green hydrogen infrastructure depends first and foremost on growing solar and wind and other zero carbon energy sources enough so that the grid is well supplied, and then we can start to use the excess to drive the electrolytic cells to produce hydrogen without any carbon at all. But if you're willing to accept some use of blue carbon for storage on the grid, even if there's some fugitive methane emissions that can't be fully trapped, although the technologies for that are very good, it's quite easy to get below, say, 1% fugitive emissions. Then that blue hydrogen is basically, once it's made, it's a carbon-free source and it's a storage source, right? Right now we're using natural gas as basically storage. It's liquid fuel. Well, hydrogen will be the same thing, except it won't put out CO2, and that will help solar and wind penetrate the grid. Right? So I think that's a great benefit because the grid is first, right? I mean, this is Electrify now. We want the grid to be green, right? And that means we need long-term storage because of the intermittency of solar and wind. So
I mean, it sounds to me like what I'm sort of taking away from what you've been saying, John, and even from the conversations we had with Professor Howarth a few weeks ago, that if it feels like there's reasons to be suspicious of blue hydrogen from the standpoint that without really fine-tuning that mechanism so that you've reduced your fugitive emissions and you're using the most efficient processes possible, you get in this position where it's like questionably valuable. But if you do what is possible, what I'm hearing from you, that if you do what is possible with that technology, it could be beneficial, at least as an interim step until we're able to do 100% green.
Yeah, I mean, we've had technologies available to reduce, and this is happening in Canada and European countries where fugitive emissions from natural gas operations are well under 1% of the total. But here in the US, it's a disaster. I mean, you're getting much higher percentages. In fact, they were underestimated for many years. So, the solution is to trap those fugitive emissions everywhere where we're still using natural gas, right? Not to use it as a reason why, well, we can't do blue hydrogen, because what that also does is that it basically gives up on all the CO2 emissions from all the hydrogen facilities until we get all the way to green, which is certainly decades away. And it's CO2 is the bigger problem, right? Methane has a half-life in the atmosphere of only 9 years. So it would go away on its own. You don't hear about methane capture technology and burial of methane, right? Because it goes away on its own. It oxidizes the CO2 in the atmosphere. So you add a very small amount of CO2 from the oxidation of the methane. So you really need to balance, and this is another criticism of that paper, they use a global warming potential, which massively overemphasizes the impact of methane and underemphasizes the legacy of CO2, right? So that needs to be taken into account. There's also other methods besides steam methane reforming. There's autothermal reforming, which is much more efficient. Coupled with CCS, it's much more efficient, uses less energy overall, and has much less in the way of residual emissions.
Yeah,
so
that's part of the reason. That's part of the problem with these labels, aren't they? Is because you kind of have to get into the. It's not just what you're doing, but it's how you're doing it, so that
it's difficult.
They're pretty sensitive to some of these different issues in terms of emissions, etc. So, all right, we probably are over time here.
Just a couple.
Joe, should we wrap up or?
Yeah, I think so. Maybe remind folks. Well, one, thank you all for coming. Remind folks tomorrow we have a webinar on regenerative agriculture
tomorrow. So we'll dive deep into land use in terms of agriculture.
Wednesday, it's on direct air capture that John already profiled. Thursday on oceans, and then Friday on sequestering at home. So join us for all those. And Brian, anything else?
Well, thank you, John, so much. That was really helpful. Really appreciate your time and your expertise. Thanks for joining us today. And thank you all who tuned in. And good luck on all of your electrification projects. If you have any questions about anything having to do with electrifying your own lives, let us know. We're happy to help. And if we can't answer, we can find somebody who will. So thanks again, everybody, and hope to see you tomorrow.
See you. Thanks, everyone.